And so we're very excited to be able to give you an introduction to this software and how it's used. So first things first, I need to sorry, everyone. I am new to Zoom. We use Teams.
Yeah, if you can snap, you can. Fine.
Okay, good. So today we are going to be talking about AMICS, which is and the applications of automated materials classification in geoscience and the materials world. So AMICS stands for Advanced Material Information and Characterization System. It's a fourth generation automated mineralogy system, but you'll notice we're using the word materials because I want you to understand that the scanning electron microscope, when properly automated, can be used for the characterization of many different types of materials, including geologic materials, like exploration materials for mining, and materials that are used for production of new materials and smelting and metals. And we'll go through all of those. Hitachi High-Tech partners with Bruker Nanoanalytics for the development of AMICS. But AMICS really originates almost 2 decades ago with Dr. Ying Gu, who was a pioneer in automated mineralogy and his original team. So the team has grown. There's been some turnover, and we've welcomed people like Chi to our team, but we also rely on a lot of our academic and industry partners to continue the development of AMICS, with the Colorado School of Mines or the University of Queensland, which hosts our major development center in Australia. So what is AMICS and what is automated materials characterization? The first and most important part of the system is that it allows the scanning electron microscope, which you may be familiar with, which uses an electron beam to generate images of materials below the resolution that would be available to a light microscope. It also uses detectors to detect the elemental composition of the material it's measuring. Now, the scanning electron microscope is traditionally used to make very nice, beautiful, but single images of samples. And that can be very useful for materials discovery and geology, and was used for many, many decades in that way. What automated materials analysis or automated mineralogy, since the geologists and mineralogists were really at the forefront of this particular field, what they really innovated here with was the addition of automation. So the ability to have these large sample holders and an automation routine that can measure the entire specimen and do it in specimen after specimen after specimen. This allows us to gather statistically significant information over a very large area. It also means that we can generate methodology to classify each of these rocks by generating a database of reference spectra and matching each individual point to that database of reference spectra. Now, you don't need to understand how this works. Anyone that's really interested in how this works, you're going to see a little bit more of it when Dr. Chi Li gives a presentation a little later. But the important thing for our discussion here to understand how automated mineralogy and materials identification is used in the industry is to understand that it translates those image data to numbers. It makes it so that we can have, yes, these beautiful false color mineral maps, right, or material maps, but also we can have real data. So we can look for trends, we can look for anomalies, and we can understand quantified our material composition. So how is this used? So first, we have a unified system. These are what these systems look like. I wanted to give you a really good image of it. This includes that scanning electron microscope, and you can see there's a big chamber right here. So the sample some specimens go in here. This is the image. This is the beam generation. It comes down. The EDS are here. These are detectors that generate the spectra. There's another detector inside of it. There's special electronics and a big. So these things are awesome. They're big pieces of equipment. But what does the data look like that it generates? So really critically, and particularly for our mining customers here, is that we're going to generate data associated with texture. So we define a grain as a contiguous area, and you can see I pulled this little particle out right here. A grain is a contiguous area identified as the same material or mineral. A particle is a contiguous area completely surrounded by background. Now, it's a little bit more complicated than that because you can see sometimes particles can touch it, they can be simple. And so we have a de-agglomeration algorithm to separate those out. And when we start to really define particles, it becomes a little bit more difficult. But the important thing here is that we can extract our grain information and our particle information, where the particle is a contiguous area that can interact with its surroundings in a free way. So this is, so we can take the first just basket or electron image, we can classify that whole area. So every color represents a different material, right? And then once we've classified the area, then we can treat these as individual particles in grains. And we can plot this as data. In this case, we're looking at grain size in microns. And so you can see we've got several samples. And this really illustrates the power of this, because we can see when our process is creating particles or acting upon particles, we can compare the process, inputs and outputs, and understand that process better. So what can you put into AMICS? And it's a really wide range of materials, right? So you can do polished thin sections, which are small amounts of glass with a bit of specimen that's been sliced very thin and placed on that glass. Mounted trunks of rocks or minerals, which can be put into an epoxy mount. In this case, you can see they're circular. Powder that's been mounted in epoxy blocks. This is probably going to be the most common way that we use it, is grains, particles, because we're interested in remembering how those particles are going to interact with their environment, whether it's putting it into an acid slurry or using it in concrete. Oh, and speaking of concrete, we can put large polished slabs in there. As you can see here, here's a polished slab of concrete that we can put in here and analyze it. And what makes us able to automate this whole process is that there's special holders that we designed specifically for the application. So you can see several of these different holders. So once again, we just put it into the sample holder. So this would be full of pucks. And in this case, they're those round pucks. If we go back, you can see there's two examples of the round pucks here and here. They would be put in this holder. And this one holds 33 samples, right? And then it goes through a measurement design process. In this case, what it would do is the stage would move, we would collect information on it from point by point by point. We then match it to that database and it creates that false colored map, right? And this is kind of what those false colored maps look like. My colleague Chi will give you more information on those and show you some examples in just a moment. So this is what I like to call the full AMICS ecosystem, everywhere where Hitachi's working. And this is a complicated diagram, but I'm just going to draw you a couple of points. And so we're going to explore this diagram and the different things that Bruker and Hitachi's program AMICS can do in these different areas so that you can understand the applications. So first, we're going to talk about this whole value chain, right? And if we think about it, it is a value chain where geologists and engineers are adding value as it moves across from this side of the screen to this side of the screen, right? Where we're going to start off looking for raw materials and exploration activity using things like remote sensing or drilling, right? Then that becomes a mine, and we have engineering designing the mine. We've got them creating a grade profile for the mine. They're going to create a block model for that mine. They're going to maintain that block model into 3 iterations. And geologic information goes into all 3 of those: the long-term plan, the multi-month plan, and the weekly plan. And that geologic information is back on the rock face or working in labs and drill face. And information can go in. Then once it's mined, it goes into stockpiles. It be mixed in the pile as it goes to grinding. The grinding is then taken into hydromet, where acid interacts with those particles, right? In all of these cases, the technical information can help increase your ability to make good decisions. Finally, after it's gone, how do we make best? Raw material makes it to the city. And we don't give up here because there's lots that we can do in the city. All that being powered. And there's really powerful ways that we can work together. So if you look on this map, number 15 is drilling. So drilling can be important for geothermal power. It can also be important to get the nitrogenous feedstocks from many of our nickel refining processes. We also have the ability to work with advanced materials like the concrete needed in number 16, which is for our, so this is for 16, which is for instance, baseload power generation or safety critical concrete applications. Finally, we're going to have incoming materials like number 14 and manufacturing of battery cells, number 12, or manufacturing advanced electronics or other sorts of things that require very fine, detailed analysis. Any material where a micron or a micrometer scale to the tens of micrometer scale contaminant cause product failure pretty much needs a scanning electron microscope to do quality control. And you can always automate that scanning electron microscope with a software like AMICS or AMICS. And then finally, we can look at the raw materials processing in like 11 and 17 ends up being products. And when those products fail, they have to go through things like defect detection. And we kind of make it all the way back to second use and refining if we look at things like is crushing them up and putting them back into the process. So let's go through this all kind of one at a time. So let's start with mineral exploration, that first. So when we're doing mineral exploration, right, we're really looking at scale and exploration risk. And our job as a geologist is really to try to refine the mineral system understanding so that we can go from the terrain scale, which is like the basin, the arc, or the region, and we can identify clusters of prospects. Trends is another word that we could use here, right? And then from those clusters of prospects, vector towards individual prospects. So we have to understand all parts of the tectonic system. And our job as geologists is to reduce the risk and try to vector from that terrain scale to the prospect scale. And then once we at the prospect scale, we can have learnings that can go back into understanding mechanisms of emplacement of ore bodies. And so this is a two-way street, right? But when we look here, we can map. Now you say, now, Jonathan, you just told me scanning electron microscopes work on the micron to tens of microns, hundreds of micron scale, not at the tens of thousands of kilometer scale. But that's not entirely true. Because when we start to look and map, and this is from a public example, right? We can look at these grains which are at the micron scale, and they can tell us about the larger environment. And we're talking about Indonesia, and I do not have a good river example. This is my good, well-published example from a glacier. So you guys don't have any glaciers, and you haven't had any glaciers in a really long time, which is really good for the world, because if you had glaciers, you wouldn't have any spectacular nickel laterite that we all know and love. But if you did have glaciers, what you would know is that glacial till looks a little like this picture, right? It's not very interesting, but it's made up of a lot of sand grains. And those sand grains were created from the mechanical action of the ice. And so where I'm sitting right now in Chicago, Illinois, just 12,000 years ago, your soils in Indonesia are millions of years old. So just 12,000 years ago, there was a mile of ice above me. Up in Canada, where Hitachi has a big office, it was up to 3 miles thick, right? So what that ice is going to do is it's going to create a dispersion profile as the ice moves over the land. And so you can see this is the dispersion from the Strange Lake deposit. So if we were mapping at this hundreds of kilometers, 10,000 kilometers, right? Or 10,000 meters, right? If we were mapping at a hundreds of kilometer scale, all we have to do is we just have to intersect that stream someplace along it to say that we are close to this strange lake intrusion. And that strange lake intrusion is a very important source of minerals in lab. Okay, so we can't really talk about what minerals, but this is the published paper, and you can probably go figure it out if you look at a geologic map. But we can see what we're going to do is we're going to identify these various materials, the various minerals in the rock, including some rocks itself, right? And we're also going to look for the geochemical signatures in those rocks at the micron scale that indicates that there's been emplacement of an ore body. So if we think about all of our ore bodies, you have to have kind of the things that have to come together, right? Whether it's time, the original source of the metal, right? Emplacement, and then we've got to have, in your case, weathering, right? So the software does this by targeting these grains. So we can take those grains as they've been collected here, and we can put them in the scanning electron microscope, and we can identify what are the materials that are in those grains, what are the elemental compositions. The geochemical indicators that indicate that we are around a source, right? And so we're working with a lot of customers to do things like automate high throughput sample preparation. We're looking at incorporating things like the micro XRF and using machine learning to identify new material resources. And there's lots of different opportunities. With every mineral system has some sort of indicator, geochemical indicator that you close. And most of the time, that's happening at the micron scale. So next we're going to go into kind of mining. And so you can see kind of the sort of things that we can do in mining. I'm going to skip over this iron ore example because Chi's going to go into this exact example detail. But I just wanted to point out here that that the software can remove artifacts. So we're only looking, we remove all the background. So we're only looking at the ore. And one of the things that we can do is we can take a look at this ore and we can classify it into types. So this used to be a very manual process where you had to look through a microscope and you had to have a geologist that was trained for years. But now we can program the scanning electron microscope with that, and a single geologist can have a much higher throughput of samples because it automatically collects the data and presents it in terms of numbers. Right? And here's an example of determining rare earth element minerals in clay. So you're in Indonesia, which is the king of clay, right? And so we can take a look at these very fine grained rocks. And I think I'm going to have Chi take a look at some of these. So you can see this is my. So we can really start to look like for some of the rare earth minerals and make the mineral maps that we need to. Moving up to mineral processing. So the copper concentration process can be, but all I want you to get from this figure is that every single one of these processing cells has both an input and an output. And so kind of what we're going to do in all of these situations is we're going to measure the input and the output of those processes. In this case, we're going to look at the crushing. So we're going to look at the starting with the big piece, commutation, which is the breaking it up into smaller minerals, and we end up with mineral, right? And then we've got stuff that we don't care about quite so much in the process. And so we want to optimize this process because the mineral crushing is one of the most energy intensive and expensive parts of the entire process. But not only that, if we overcrush our rocks, it becomes very, very difficult to dewater that, right? So we have to make sure that we're not taking it too small, but we are making it small enough that we can extract enough of the mineral. And so you can see here, this is a single mineral that's been exposed, and this mineral has then has waste associated with it, and then the process. So if we look at this chart, we talk about liberation. So 100% liberated means you just have the minerals you're looking for. And 0% liberated means those minerals are completely encased in something else, no free area, right? And so it's easier to recover the more liberated it is, but that also usually ends up being the smaller it is and the harder it is to dewater and the more energy it took to get there. So automated mineralogy is really used to take a look at those particles, and we can see here's the 100% liberated, and we can see here's the 0% liberated. That means there's nothing we care about, or it's completely surrounded by other materials. And so what this really tells us is that if we're only getting we can evaluate how much of our sample is going to be completely liberated. These are the ones that can then be extracted using hydrometallurgy or flotation, right? Concentration processes, right? And that's going to be the key to optimizing these processes. And you can only make that decision if you're looking at those grains at the scale that the mineral processes happen at. So, of course, we have, in all situations, we have a feed that comes into the system, right? We have the concentrate that comes out, and we have the tails. So we can actually reconcile the whole system with just 3 measurements, and we can understand how our processing flows are working. So every single point in the mineral processing system can be analyzed. And this is why AMICS has to be so fast, because we have to be able to take many different replicas from many different cells along a mineral processing. So let's go over into some materials before I hand it over to Dr. Lee. So this is one of my favorites. It's polymer concrete. So we got to talk about the ability to look at new materials. So this is a concrete that's been created by using geopolymers. And so I highly recommend this paper. We're going to distribute these slides when we're done. This is an excellent example of how new material discovery, and it helps us understand where does the polymers go and what's the texture of that material. So this is slag, so large area mapping on slag. Look at the scale of this, 15 millimeters by 5 millimeters, right? And we can see here's the slag image, BSE, mineral, and EDS map. So we can look at the elemental composition here as well. An iron sinter, and you can see we can separate it based on not just the material identified, but we can classify the particles themselves based on the distribution of the phases within the particles. Here's more of that absolutely gorgeous slag analysis. We can even target the impurities in this to understand what is our risk. We can calculate acid mine drainage by understanding our acid generating potential based on surface area and understand the contaminants and the future long-term environmental consequences of storing these things. This is a great example. This is black mass. This is, like we said, multiple measurements, being able to understand the difference between measurements, how the elemental compositions vary, and what the recovery potential is. Black mass is ground up battery material. And so this is like a brand new ore. And what's really interesting about this brand new ore is think about all the electric cars that are being imported into your country right now. That's like a mine where they're shipping the ore to you every single day. You just have to wait for those batteries to run out, and that's a great opportunity. And so this means that we can start to have a circular economy that recovers everything from graphite to lithium. Very exciting. And then finally, I just wanted to give you some examples from steel before I pass it over to Chi. So here's the stitched BSE image. It's not very interesting, but what we can see is we can get sub-micron particles where we can understand the cleanliness and contamination of the steel, and not just how much it is with image analysis, but what those contaminants actually are, which is very exciting for steel analysis. So here's an example where we can see, here's the size in microns, and we can see the difference between the magnesium steel and the calcium steel, how many particles are there, and the size fraction distribution of those particles in the steel. And pore analysis as well, right there from within. So here's precipitates, here's some pore analysis from steel, also absolutely excellent data. And so we can extract what are the pores, what is the pore distribution, the size, and the aspect ratio of those pores. And she's going to hand it over. We're going to talk about drilling, but I just wanted to give a quick preview here. Here is our drilling. When we drill down, the material is going to come to the surface, and the scanning electron microscope is our only opportunity to have real quantitative data from the surface. So I'm going to stop sharing. I hope that I didn't scare everyone. And I'm going to hand it over to my colleague.
Thanks for that, Jonathan. I thought today what I would do is actually, since Jonathan spent a fair bit of time about mineral liberation, is we'll start looking at, I guess, an easy case of how AMICS can provide meaningful information. And that's in copper, concentrating copper. And there's obviously with electric vehicles and the change over to an electric economy, copper is going to become ever more important. So here is actually AMICS process, real data that you can see here, hopefully. But I think Jonathan mentioned the fact that you can actually clean up the data. So one of the first things you notice is that what we can actually do is we can switch between the two image modes. This is actually the BSE. And so AMICS will actually always retain a high resolution BSE image. So you can interrogate your sample to better understand what it looks like as if you were in front of the SEM initially. But it's not just that. Every single point that we collected X-rays on, we have a record of it. And so we can actually interrogate every X-ray point and understand what elements were present, what peaks, the peak shapes were there to actually understand why it was identified and characterized the way it is. And that's the power of automated mineralogy and AMICS in the fact that post-analysis, you still have access to all the data. So the first thing you notice here is that in this particular sample, the user has accidentally analyzed a bit of the actual holder itself. And like I said, beautiful thing about automated mineralogy AMICS is if I don't want that, it's just as easy. Just select the area that I'm not interested in, even these little grains here and these ones here, and tell the machine, hey, I'm not interested in those. Could you get rid of them? Give it a bit of time. My computer has a few things open and it's gone. And now we can get rid of some of that detritus from the actual analysis. And so you're not going back and actually doing the analysis again. The false colored image you see here is basically AMICS comparing all the spectral data that we collected to a list that we've generated in the past of known materials. And so our target is obviously the copper sulfides. And mixed in all the purple there, if we want to sort of highlight the purple and see exactly where it is, we can highlight it and really pull out all the details. But it's not just about visualizing the data. We obviously need to create tables or feed numerical values into our models. And so that's where we have calculation tables, where we can have a look at the mode of mineralogy, so we know the general composition of the material we're looking through, all the way through to what we're looking at before at the particle level. To all the liberation and locking information. So we can look at how well the material is locked and liberated, and we can even visualize what those particles look like. And so now we can sort of get a better understanding. If we're looking for gold or if we're looking for copper sulfides, we can understand the morphology of the actual material that we're looking at. So the modal through to, if we want to look at liberation, in maybe let's do 25%, I can see the well-liberated materials or the copper sulfides all the way through to the unliberated materials here, which is obviously a majority of your gang. And so you don't just get data, which can be fed in a model, you can now actually visually see what the material looks like. And one thing that we didn't mention is because automated mineralogy is an automated tool that will actually scan your whole sample for you, in many cases, copper sulfides or copper ore bodies, you may find some precious metals. And in this case, you can probably see that there's a small amount of gold present in these particular concentrates. And if you are interested in understanding the gold, you don't have to go search for it anymore. You can just tell the machine to find that gold for you and try to find where it's isolated. And you can see here, it's all sitting in the iron sulfides. And so we know straight away that if we're trying to recover any of the gold in this concentrate, we're also going to have to extract a lot of the pyrite from the material as well. And so it automatically gives you a very quick understanding that maybe the gold is non-recoverable because it's too heavily embedded in the iron sulfides. And you'll end up with a lot of iron sulfide, and you really don't want to be processing and creating acid at the same time. And so that's the power of automated mineralogy and the sort of information that it can give you at the comminution stage, at the hydromet stage, at the acid leaching stage. And so it's giving you all the information you need to make critical decisions at the plant when you need them. So apart from copper, which is where a lot of automated mineralogical machines are used, if we now look at, I won't save any of the changes there, back to that iron ore sample, here's that exact same sample. Again, you have access to that beautiful high resolution BSC image. So you can actually see the different textures and different materials already just based on the grayscale. But as always, we can use the X-ray data to classify the material. And now we have a better understanding, not just visually on the BSE what it is, but chemically, we've been able to separate out three main phases in terms of hematite, magnetite, and goethite. So this is basically a mixed ore that the client was looking at, and we can see that it contains iron oxide goethite, it contains here hematite, and it contains here magnetite. And we can do this separation because every single point, as we said before, you can see how many points we've collected contains spectrum. And so we can actually interrogate this spectra post-acquisition to actually look at the iron-oxygen ratio and use that as a means of separation of the different materials. In addition to, if we look at the goethite, we can see that the goethite is a little bit dirty. And so they do have deleterious elements scattered throughout the actual material. Again, that is critical information if you're receiving ore and that's going into your blast furnace. So apart from understanding the particle size of the material that you're getting, you'll also understand the actual composition of the different particle sizes. And so that might give you an ability to further upgrade the material by removing the goethite, treating it separately, or blending it and creating pellets. So if you do get this mixed phase ore, a lot of blast furnaces will basically render this into pellets and feed the pellets in, where they can control the actual elements that they're actually feeding in. And automated mineralogy, automated material characterization, it doesn't have to be a mineral anymore. If the material has been sintered and crushed and grind, you can look at the pellets well. So here is something I prepared earlier. This is actually pellets that were prepared from that material. So they've taken the material, the incoming, they've crushed it, ground it, pelletized it in preparation for blast furnace introduction, but they can also now understand how good was the pelletization in terms of removing some of the deleterious elements. In this case, probably not so good, because for some reason they've also incorporated chunks of quartz all throughout the pellet, which is obviously going to be an issue for them. But at least now they know, and they can adjust their process and understand where the actual quartz came from to actually prove the product that they're actually introducing into their blast furnace. And so you can see the versatility of AMICS as a tool from all points of the life cycle of your process, from the material coming in, post-processing, and as Jonathan showed you before, even after you've actually created the steel, you can actually look at the steel and have a look at the contaminants that have actually accumulated on the steel, again, to backtrack and improve the actual performance of your process. So apart from iron ore, so now we just move a little bit away from mining. Here, everything you've seen at the moment has been, I guess you could say, coarse grain material. So nicely mineralized material that you're going to crush iron and prepare, but limited to only looking at all those coarse grain materials. We can also have a look at clays. Again, I've worked with a lot of nickel laterites and had to deal with a lot of clays, but also working in oil and gas, clays are always present everywhere we're looking. And so what I'm showing you here is actually a sample of a core plug taken from a piece of core from a mudstone reservoir. All the green you see there is your illite muscovite, But what you notice is that we can actually start picking up details within this core space where there's actually bands of carbonates running through. In addition to a higher sand load at the top of this core compared to the bottom, plus the actual, because we're not just doing elemental composition, we can actually now look not just at the fact that there is sand at the top of the core, but we can actually look at the grain size, and visually you can see that there are coarser grains at the top compared to the much finer material at the base. And so you can start looking at the material not just in terms of composition, but you can also now look at it in terms of its morphology and understand exactly how this was deposited over time. And that will give you an indication, or at least give you some indications of potential reservoirs. What you also notice, the black area here, if we turn this off, all of those pores or cracks that are running through the system, we can also characterize. And so the data isn't wasted. Even though it's an open space, we understand that this is actually open space, but AMICS actually recognizes it as porosity. And so from that one analysis of this core piece, you're not just getting the mineralogy, you're also getting the morphology. So you get the grain size, you get the grain shape within the sample. But now you also get an understand of the porosity, and not just the porosity, but also the actual pore shape as well. So we can pull the porosity out and actually analyze it as if it was a mineral and understand if it's elongated, rounded pores, connected pores. And again, that's going to give you an indication of the reservoir quality that you're dealing with in this particular material. One thing a lot of oil and gas people appreciate with AMICS is because it's a very consistent analytical tool, every data that you collect from a particular project is compared to the same mineral library, which means you're getting very consistent quantification or characterization of your material. So if you measure cuttings or cores up and down the length, you can generate a very, very consistent core log. And so in this case, for example here, you can generate a core log like this. And zoom in. There we go. Where all the mineralogy is collected consistently up and down your actual core. You can look at individual minerals to understand trends throughout that core volume. And because you have the mineral volume, you also have the porosity, you have the ability then to start predicting petrophysical properties as well. And so you can actually start using it to do some predictions of your gas via your shear velocity, your compressional velocity, and from there, Young's modulus and Poisson's ratio. So there's a lot of versatility in the data that you're from this single analysis. Obviously, a lot of single analyses, but consistently collected over the length of the core, it gives you a really good understanding of what you're looking at in the actual sample itself. For those of you who are not working in the minerals mining, natural resources, and pure geology, then you also have the luxury of time to then sit there and collect beautiful images like this. This nice basalt, where you can really start looking at the texture. If we go into raw library, we shrink it down. So we can see here, not big Hawkeye grains. We can see chlorite intrusions running through your system. And again, all of this data is available to you. It's available all the time, and which means everyone can see and interpret the data with you as opposed to just looking at a series of numbers. So I just wanted to, hopefully that sort of showed you the flexibility of AMICS in terms of the different materials that you can actually analyze and interpret. But yeah, if you want to know more, get you in front of a machine, get some samples, and really sit down and show you what AMICS can and how it can actually fit into your workflow to answer the questions that you want. And I want to make sure that there's enough time for questions, so I'm gonna sort of stop there.
Yuchi, thank you so much. So I think we can hand it over to the moderator if he wants to open up the floor for questions.
Okay, thank you, Mr. Knapp, for the informative session. Now let's proceed to the Q&A. You may type your questions in the chat or raise your hand as the to
So if no one's going to raise their hand to start, I'll start off by asking Chi a question. So Chi, you showed some examples of very fine rocks that you called mud rocks. Can you put some context of what that would mean for looking at something like a nickel laterite in an SEM?
In fact, I ran a huge project during the nickel boom, looking exactly at nickel laterites. The beauty of the SCM is that you're getting chemical data in association with the clays. And so, as we all know, the nickel is not mineralized in nickel laterite. And so you can actually use the chemical signature at that micron level to actually speciate out your barren clay to your nickel pregnant clays. So it's actually the perfect tool for that to actually do it. Still muted.
Please continue. Untuk teman-teman kalau misalkan itu nanti akan kami bantu untuk translation. Kasih.
This question. So I will start reading the question and then I will respond. So the question is, would like to know about the type of data that is most influential in prediction models to determine the availability and quality of battery materials. Also, can you explain how data is usually collected and integrated into the model to ensure accurate predictions? Okay, so to be clear, AMICS is a data collection tool. So it is not making predictions. We have other software that's used to help make predictions and other tools to help make predictions using machine learning. And what I have learned from doing a bit of machine learning, I'm not a super big expert, right? But I'm starting to learn more and I'm doing some more, is that every system, the sensitive variables are going to be different, right? And it depends on the data you're collecting. But what is very, very important is the consistency of collecting that data. So if you're going to use image data, which is critical for exploration for battery minerals, because we look at textures of the laterites, texture of the rocks, right? We have to make sure that we have a system that's collecting the data in the same way every single time, right? And so one of the things that AMICS can do when we're doing a lot of these exploration, we're doing particle analysis. And what we care about is not necessarily the minerals, but we care about the rock, the lithology. And lithology is a collection of minerals, but not always the same and in different proportions. So you have to look at the proportions and those sorts of things. But what we can do with AMICS is we can sort those particles and we can export the images all in the same way and to collect it all in the same way so that they can be used for training of machine learning models. And so we're very cognizant of the machine learning end-to-end data pipeline. And we have lots of tools. Come talk to us about Hitachi Materials Informatics, right? We'd love to talk about these products, right? Platforms for AI. We're world experts in AI models. We're really excited about this, but we have to think a lot about that pipeline, all the way from data collection and making sure that we get the right metadata when we're doing the data collection in the field. Scanning electron microscope, the agent that extracts the data and exports it and brings it to the cloud for the end-to-end data pipeline. Now, very importantly, is the next question. Also, can you explain how data is usually collected and integrated into the model to ensure accurate predictions? So the name of the game for everything we do has quality control. And what's important about what AMICS is doing is that because it's using programmatic approach instead of a machine learning model-based approach to that first level, right? It's going to be data. So when we have new materials or minerals that show up, it shows up in terms of being an unknown. And so we have to go back into the system, add new standards from our data. We don't have to go to it. We don't have to find standards. We can generate that from our data. And then the model gets better. The classification model gets better, right? And because that is a programmatic approach, we're using the physical and chemical characteristics of the materials themselves in its classification. That can be used with confidence to train models, right? So this is all kind of the base of the pyramid. You've got to have the training data, right, for machine learning models. This is the base of the pyramid. This is how you generate your training data. I hope that answers the question. There was another question, I think.
Maybe
They retracted.
Sandra, can you send the questions, please?
If we have no more questions, we're right on time, moderator, so it's up to you. Yeah. So automated mineralogy is the automation of a scanning electron microscope to collect data over the entire sample. So what it's doing is it's going to be automating the actual SEM, and it's going to be collecting data in every point. And so because it's automating the whole thing, we can then compare that to a model, identify all the materials in the sample, and generate graphs and charts of the material.
Okay, Mr. Knapp, you can answer from Afifa first. There's another question.
So the question here is, I would like to ask about how significant is the role of a mining engineer in making decisions based on the results generated by AMICS? If the output produced by AMICS is sufficiently accurate, does it eliminate the need for human assistance? And the human will always play a role in the decision making. AMICS is a tool for collecting data and generating information. It's not there to make decisions. The human is always there as that final port of call in terms of AMICS, right? You don't know in the future if there's going to be some AI model that sort of supersedes us, but AMICS definitely is not there to replace people. It's there to assist people in making their decision.
Exactly, Jim. You can't underestimate the need for expertise. And what this does is it frees up the experts like data scientists and geologists to take the next step, which brings us to another one of our questions here. What is the potential implications of AMICS and renewable energy sectors, especially with the rising demand? So this software helps us find more minerals. And once we find those minerals, it helps us extract them more efficiently. And once we've extracted those more efficiently and produce them more efficiently, when we make batteries, which we'll be making batteries everywhere in the world soon, it helps us produce those safer because there's less contaminants. And when it comes time to recycle those batteries, what it does is it's going to allow us to treat that recycled battery material, that black mass, like a new ore and put it back into the process to be a circular economy. So it's useful in every step along the way. So it will be helpful in creating more materials. You want to take the next one, Chi?
Yeah, so the next one is I would like to ask how important is the role of machine learning in evaluating the performance of materials in geoscience exploration results. I think machine learning is progressively becoming a more useful tool. And I always say tool. Again, I step back. It should never be the final decision maker. Machine learning is a really, really good tool for finding patterns and understanding patterns that as a human sometimes we miss because there's too much data, right? So it is there as a tool to help us find new prospects that maybe we didn't see before. So again, it's about focusing the expertise and that experience that is us, the people, on making those critical decisions as opposed to doing the grind work. I mean, that's what the machine's there for. That's what AMICS is there for, is to give, they're there to give us a compressed, concentrated set of information so that we can focus our minds, focus our experience on making good decisions with that data that we've received, information that we've received.
And this goes back to, I think we had another question here from Salwa, which is about how AMICS can be used in those data models, right? AMICS is going to largely be the training for those data models, but also you can start to look at predictive analytics when we start to have trend data. So if we go back and think about the exploration data, collecting data over very large areas, predictive analytics can help us predict anomalies from very subtle variations in the mineral chemistry and inclusion chemistry. The other thing is that when we're operating a mill, predictive analytics can start to identify when those mills start to go out of variance sooner, right? And so one of the traditional, like we can take a lot of the ways these predictive analytical models that are currently being used with just like bearing temperature and things like that in these large mills, and we can actually look at their outputs to understand how the whole system is performing and to start to identify when we start to have variances, changes in the slope of the curve, right? That can tell us either there's something different about our input, but we measure the input, or there's something different about our machine, so we can optimize it.
So the next one's a quick one. I would like to ask if there is any significant difference in the use of AMICS for different. It skipped up. Oh, where's it gone? No, differences in the use of AMICS for different types of materials, such as metallic versus non-metallic. Ultimately, there's only a few requirements at the moment for AMICS. Is that for the SCM purposes, it needs to be obviously suitable for a vacuum chamber. Though saying that, there is the option of running AMICS on a micro XRF, the M4 from Brooker, which doesn't need a vacuum. There are limitations on that. We won't go into details. On top of that, there's always a limitation in terms of, with X-rays, the elements that you can see. We're never going to be able to see ultralight elements. People keep asking, can we measure it? Exactly, right? And the answer, unfortunately, is no. So there are limitations to it, but in terms of the material, as long as it fits within those limitations, you can do metallic, non-metallic, man-made, extraterrestrial, meteorites, anything.
So I'm just going to jump in here and answer this question because I love to get questions from geophysicists because she's originally a geophysicist, right? Mm-hmm. And this is the ultimate geophysicist question, which is, are there any challenges that could hinder the collection of geoscience exploration data? And as a field geologist, I always have to explain to Chi, you got to buy hiking boots to be a geologist. And so if you have a chance as a geophysicist, go get some hiking boots on and go with the geologist out in the field, right? I know that sometimes you guys get to walk across the jungle and put the sonophones out, but go in the field. And so the biggest challenge about geoscience exploration data is getting the samples, because you have to put boots on the ground to go out there and shovels in the dirt. So that's my answer for the biggest challenge.
That's why we have geologists. We stay in the office.
Don't worry, she does have good hiking boots. We've
Yeah, I do.
he just usually brings his dog along.
Yeah.
Do you want to take that last one, Chief?
Okay, where is it? I'd like to ask a question: how the implementation of automated mineralogy AMICS enhance data-driven decision making in geoscience and battery material, particularly in the context of machine. So a lot of this, so machine learning, predictive models, right? The one thing everyone needs to be aware of, and I'm sure a lot of our viewers today and attendees today know, is that they need a lot of data, right? They are driven, it's a data-driven technique, machine learning, AI, and the beauty, and it's just not any data, right? And that's a mistake people make, is that they just say, oh, big data, I'll just grab any data, put it together and get it. It doesn't have, it has to be consistent, it has to be well-ordered data. And so that's the beauty of AMICS, is that all the data you collect is consistent, it's traceable, so you know exactly where it comes from. And so you can feed huge amounts of data, because we can collect data quickly on AMIC systems to feed into your machine learning models and your predictive models, and be confident that you're not introducing errors in your predictions.
It was excellent. Thank you, everyone, for the excellent questions. We appreciate your participation.
Okay, the conversation has concluded. As Mr. Knapp and Dr. Lee previously mentioned, AMICS is a powerful tool that streamlines the analysis of minerals through three key steps: automating data collection using innovative hardware and software, reducing and classifying the data to identify minerals and generate detailed mineral maps, and quantifying image data for statistical analysis. These results are crucial for decision making and reporting in mining, and how we would process them. Now I hand it back to the master of ceremony.
Okay, thank you, moderator, and thank you so much for Mr. Jonathan Knapp and Dr. Lee for the presentation. For all audience, you can take a break and fill in the attendance list in the column comments on the Zoom meeting with a time limit of 5 minutes. In this first season, we know that AMICS, or Advanced Material Identification and Characterization System, is a fourth-generation automated mineralogy system jointly developed by Bruker Nano Analytics and Hitachi High-Tech Canada, with local support and development provided by global partner. Okay, next presentation is by the second speaker, Mr. Irfan Ibrahim, who will present to us automated mineralogy for copper sulfate mineral liberation and characterization. For the moderators, time is yours.
Now, welcome to the last session of our main event. In this session, Mr. Ibrahim will be presenting about the case study of using AMICS in copper sulfide. Before we start, I'll remind the standard operation procedure for the participants. During the presentation of the material, participants are prohibited from interrupting the speaker. During the event, each participant's video camera must remain on and use the virtual background provided by the organizing committee. When the speaker is delivering the material, each participant's microphone must be turned off. Unless when participants wish to express their opinion or ask a question, they might use the raise hand or chat feature first. After being given permission by the moderator, they may turn on the microphone. Now, it is my pleasure to introduce our speaker, Mr. Ivan Ibrahim. Mr. Ivan holds a bachelor's degree in geological engineering from Universitas Trisakti and has extensive experience in the field of geoscience. He started his career as a junior geologist at Trisakti, followed by role as an SEM specialist at Geoservices Limited and as an engineer at Asa Prima Energy. Currently, Mr. Ivan serves as a mineralogy supervisor at Geoservice, where he specializes in rocks and minerals, particularly in the mining, oil, and sectors. His expertise in project and operational management makes him a valuable asset to the industry. We are honored to have him with us today to share his knowledge and insights. Uh, and for this session, we will using Indonesian. Untuk Bapak Irfan Ibrahim, waktu dan tempat saya persilahkan.
Oke, selamat pagi semuanya. Suara saya cukup clear?
Ya, clear Pak. Selamat pagi.
So, I got my boss here. Wayne, morning. Jonathan. How do you do? How things going on, man? I apologize, my camera is dysfunction currently. And I'm going to deliver in bahasa. Terima kasih semuanya. Sebelumnya Hitachi, terima kasih. Geoservice, terima kasih. Dan juga Itera, Bapak Ibu sekalian yang sudah hadir dalam presentasi singkat ini. Jadi saya coba menambahkan sih sebetulnya dari past experience kami sebagai satu-satunya commercial lab yang menggunakan Automated Mineralogy System AMICS terutama ya. Dalam hal ini saya coba sampaikan dalam bentuk case study, liberation study. Jonathan just spoiled my surprise as I want to share about petrography on AMICS later on. Masuk kah?
Ya, kelihatan Pak.
Oke. Saya sebelumnya ini hanya ingin memberikan case study karena sepertinya Ci juga sudah memberikan contoh ya, contoh penggunaan. Mungkin beberapa dari kita belum familiar terkait apa sih itu automated mineralogy. In 2016, jadi di 2016 itu saya kebetulan tugas akhir menggunakan SEM. Namun yang saya tahu itu SEM hanya berdasarkan imaging saja, gambar, karena basisnya SEM ini mikroskop. Cuma kalau kita kenal mikroskop itu kan cahayanya baik polarisasi maupun refraksi. Kalau SEM ini dia ditembak elektron. Dan juga ditambahkan dengan EDS untuk chemical analysis-nya. Dan pada 2018 ketika saya pertama kali bergabung ke Geoservice, a whole new world buat saya ketika saya mengenal automated mineralogy. So, hari ini outline saya akan membatasi agar tidak overwhelmed, tidak terlalu banyak informasi, supaya kita berkenalan dulu apa ini sih barang ini, apa automated mineralogy itu apa, berdasarkan case study yang kami punya. Lalu saya remind lagi what is automated mineralogy, lalu kita ke liberation study case dan a sneak peek. Presentasi ini sebetulnya hanya untuk memberikan pengenalan singkat tambahan sebetulnya, karena presentasi dari Jonathan tadi dan juga Ci sudah sangat lengkap mengenai automated mineralogy ya, terutama AMICS. Dan case ini saya untuk mengkarakterisasi sebetulnya dalam tembaga sulfida. Jadi AMICS ini memberikan sebetulnya banyak sekali data dari nama mineral, elemen deportment, lalu derajat librasi, lalu ada ukuran butir, bahkan rate recovery, mineral asosiasi, juga bisa diberikan oleh AMICS. Nah, banyak yang bertanya sebetulnya nama mineral kan bisa dari unit lain misalkan seperti XRD. Namun di AMICS Automated Mineralogy System ini kita data yang di set itu lebih banyak untuk kata kunci dari C tadi itu adalah optimasi untuk beberapa lini masa dari sektor misalkan tambang. So let's dive in. Kita kenalan dulu. Kita remind lagi apa itu automated mineralogy. So what is automated mineralogy in a nutshell? Jadi beberapa publikasi itu sebetulnya tidak mendefinisikan automated mineralogy secara spesifik. Contohnya shows tahun 2020 dalam publikasinya memang tidak ada terminologi khusus. Namun berdasarkan pengalaman kami, automated mineralogy itu sebenarnya same base system yang memberikan data yang sangat banyak sebetulnya. Termasuk seperti yang saya bilang tadi, mineral abundance, persentase, element of interest, concentration. Jadi element of interest concentration ini misalkan 10% tembaga dalam satu sampel, itu yang menyumbangsinya mineral apa saja dan masing-masing mineral berapa persen. Misal Covalent hadir, chalcopyrite hadir, bornite hadir, nah masing-masing sumbangsinya berapa persen ini terhadap si total CU. Lalu ukuran butir per mineral pun, lalu asosiasi mineral yang mana esensial ketika kita berbicara terkait mineral alterasi, lalu juga terkait weather mineral terhadap current mineralnya, lalu derajat librasi dan juga lockingnya, bahkan grade recovery. Salah satunya yang jadi rutin ya di geoservice terutama itu sebetulnya adalah bagaimana kita bisa menggunakan ini di
Maaf Pak Ibrahim, kayaknya PowerPoint-nya nggak jalan sih Pak, masih di page pertama.
memang masih sorry.
Oh, ya. Ya, udah.
Oke. Jadi ini memang saya lanjutkan ya. Menggunakan automated mineralogy system ini untuk mengoptimasi di proses metallurgi ini. Dan kalau kita backtrack di fase awal industri ini sebetulnya juga kita bisa tahu natural occurrence dari hubungan antar mineral. Nah, itu juga bisa dikategorisasi dengan automated mineralogy. Dan saya cerita tadi sebelumnya saya berkenalan dengan semidias itu kan hanya imaging ya, hanya gambar. Dan automated mineralogy ini sebetulnya adalah upscale. Jadi kalau kita main di SEM biasa, itu kan hanya gambar, lalu ditembak EDS per titik tembak aja. Nah, kita menentukan, oh ini mineral apa, itu berdasarkan struktur kristal, lalu dihubungkan atau dilihat ke referensi, lalu spektra dari IDS-nya kita lihat dari referensi juga, cocoknya, oh ini mineral ini. Gitu. Lalu bisa nggak kita bisa menentukan mineralnya secara otomatis nggak? Tentu bisa dengan sistem ini gitu. Jadi ini an upscale. From qualitative perspektif jadi tergantung pengamat yang punya gambar kita lihat oh ini mineral ini. Sekarang kita based on system dan goes to quantitative technique. Sampelnya apa aja sih sebetulnya seperti yang tadi Jonathan cerita ya. Itu dari polish block bisa grinded sample ukuran serbuk. Beberapa case itu bisa di chips, rock yang sudah di slab ya, dalam permukaan. Lalu juga di thin section. Yes, jadi kalau di biologi kita belajar petrografi itu kan sebetulnya kita berdasarkan sifat optis ya dari mineral sendiri. Nah, kita upscale, kita bantu dengan penentuan dan kuantifikasi mineralnya itu dengan sistem Automated Mineralogy AMICS. Ini contoh hasilnya. Yang atas yang hitam putih itu bagaimana backscatter electron image. Kita lihat mineral copper sulfide-nya bebas atau sulfide yang lainnya masih terikat, atau saya biasa bilangnya biar gampang ya, mineral sulfide ini masih dipeluk atau udah bebas. Dan yang kanan ini false color image berdasarkan determinasi menggunakan AMICS tadi. Dan kiri adalah facility kami.
Sorry Pak Ivan, interrupt. Ini belum berubah gambarnya Pak Ivan.
Gitu. Sudah masuk?
Masih belum, Pak.
Coba share. Reshare. Sudah masuk sampai sini?
Masih yang what is automated mineralogy nih Pak.
Ya,
Iya, masih di situ.
mungkin bisa kita bantu share screen aja, Pak.
Boleh, boleh.
Oke.
Saya stop share dulu ya.
Ya, Pak.
Oke, selanjutnya. Kalau kita lihat penentuan mineral itu kan sebelumnya kasarnya ya mengawang-awang. Oke, ini ada heavy mineral, ada light mineral. Lalu bagaimana kalau kita punya sistem yang bisa menentukan secara definite mineral ini apa gitu. Nah, jadi automated mineralogy system ini kita X-ray dan masing-masing itu di masing-masing mineral itu punya typical X-ray, spektrum masing-masing yang kita compare ke database dari AMICS sendiri. Dan ini adalah hasil false color yang mineral-mineral tersebut sudah ditentukan. Oke, boleh next. Lalu kita coba lihat lebih dalam kalau di liberation study itu dalam hal ini kita case-nya di ukuran ya, size by size samples. Boleh next. So, what is a liberation study case? Sebenarnya liberation itu apa sih? Jadi dia itu free surface. Jadi kata kuncinya free surface yang dikuantifikasi oleh sistem. Dalam hal ini kita coba di ukuran 300, 180, plus 75, dan minus 75. Nah, dataset yang saya coba hadirkan supaya tidak terlalu membludak ya. Karena kita masih kenalan terhadap automated. Itu hanya di nama mineral dan jumlahnya, lalu elemen department atau yang saya cerita sumbang sih tadi, lalu liberation data dan grain size. Jadi masing-masing dataset yang kita coba hadirkan itu untuk memberikan gambaran komprehensif terhadap ini loh behavior dari mineral itu sendiri ketika kita treatment something. Liberation secara gampang itu kita lihat di gambar yang baru saja tampil. Saya bilangnya masih udah dipeluk atau masih bebas nih. Masih dipeluk atau sudah bebas. Jadi dia dalam degree, dalam ranging angka. Apakah dia sudah total bebas 80 sampai 100% atau dia surface-nya itu sepenuhnya masih dipeluk. Atau mulai pelan-pelan lepas nih. Oke, next. Untuk mengetahui mineral apa aja sih sebetulnya? Karena ini kan relation dari mineral pengotor dan juga mineral biji atau mineral target gitu. Jadi kita kenal dulu penyusunnya apa aja. Kita lihat dari list mineral di slide selanjutnya. Jadi di sini mineral-mineral yang terkomposisi ada beberapa 12 mineral khususnya yang other materials atau other minerals itu yang less than 1%. Karena supaya tidak long listed. Nah, di sini kita lihat ada chalcopyrite dan covellite itu sebagai mineral target walaupun hadirnya juga kecil-kecil ya, below 0.5. Lalu ada mineral-mineral pengotor seperti clay dengan tipe-tipe yang bisa spesifik bisa ditentukan oleh AMICS dalam hal ini, lalu pirit dan juga kuarsa. Oke, next. Lalu kontribusinya dari masing-masing mineral itu terhadap elemen bagaimana gitu. Mungkin sebelumnya di presentasinya Jonathan sempat menyinggung terkait deportment. Nah, ini bahasa lainnya adalah elemen deportment. So, next. Next. Nah, ini kita lihat di sampel pertama kita punya, back. Itu ada di sampel pertama terkonsentrasi 0,2 koper. Nah, siapa nih penyumbang kopernya sendiri? Ternyata 0,1-nya atau setengahnya itu dari coflite saja. Lalu 0,1 di sampel terakhir itu full dari coflite saja. Kita juga bisa tahu dari mineral-mineral lain sumbangsinya terhadap elemen tertentu itu bagaimana. Misal, supaya lebih ada gambaran lagi nih, total silika dalam sampel pertama itu sekitar 29,3 ya, itu. Nah, konsentrasinya. Siapa aja sih yang ngasih kue sebesar 29,3 itu, potongan sebesar 24,4-nya itu disumbangkan oleh kuarsa. 4,2-nya disumbangkan oleh pyrophyllite dan sebagainya. Jadi itu kita data-data yang bisa kita karakterisasi melalui sistem ini. Oke, next. Kita lihat apa sih kalau di case study aslinya itu gambaran tentang mineral-mineral yang terkunci atau sudah bebasnya kayak gimana gitu. So let's dive deeper. Next. Nah, ini di gambar kiri paling atas itu ukuran 300, lanjut ke clockwise ya. 180 di kanan, plus 75 yang kiri bawah, minus 75 yang paling kanan bawah. Nah, ini kita lihat beberapa mineral itu fully lock di contohnya pirit dan copper sulfide ya. Copper sulfide ini saya gabung karena ukurannya terlalu kecil kalau ngeliat chalco dan coflite-nya. Jadi saya gabung satu aja dalam lingkaran merah. Nah, lingkaran kuning ini saya pirit karena lebih besar supaya memberikan gambaran, oh ini barangnya, oh ini arti dipeluknya gitu. Nah, itu dilihat piritnya masih di tengah-tengah si kuarsa sebagai pengotor. Oh, si copper sulfide-nya juga ada yang masih di tengah-tengah kuarsa misalkan, atau berikatan juga dengan si alunite kayak gitu. Lalu ke size yang mulai dihaluskan lagi, mulai geser nih, mulai bebas spiritnya, copper sulfide-nya mulai bebas kayak gitu. Jadi memang as mentioned by Jonathan, kita pengen tahu nih, jangan sampai terlalu halus atau di size berapa yang paling efektif. Oke, next. Kita coba memberikan gambaran lagi nih. Kalau pakai bar chart kayak gimana? Merah nih full masih dipeluk, biru mulai bebas. Nah, kita lihat di gambar itu kan ada yang copper sulfide-nya setengah-setengah tuh, setengah-setengah mulai bebas. Ada yang masih dipeluk. Gitu. Ada juga yang size kecil itu biru itu yang contoh udah bebas. Nah, ada juga pirit yang setengah-setengah di gambar terakhir. Middlings istilahnya. Oke, lanjut. Lalu AMICS sebagai salah satu sistem automated mineralogy juga bisa memberikan data ukuran butir. Pada slide selanjutnya itu adalah ukuran butir. Boleh next. Dari keseluruhan sampel. Kita lihat ternyata paling besar itu di 400 yang retain ya. Itu di 400 mikron, lalu makin halus. Untuk next slide-nya please. Nah, ini ukuran butir dari masing-masing mineral. ternyata covellite sendiri di sampel pertama itu tuh ukurannya bisa sampai 37,5 mikron. Lalu ada chalcopyrite yang variasinya masih semuanya di bawah 10 mikron. Kita bisa mengetahui ini dari automated system. Gitu. Jadi datasetnya memang banyak. Oke, lanjut. Jadi dari penjabaran singkat kali ya menurut saya terkait beberapa dataset. Jadi kita bisa tahu nih CO concentration itu sebenarnya paling tinggi kan di sampel pertama. Tapi dia masih dipeluk nih gitu. Kenapa? Oh, dia datanya besar karena dia ukurannya juga besar. Lalu yang bebas itu ukurannya udah kecil-kecil. Sementara chalcopyrite paling bebas itu di minus 75 dengan ukuran minus 5,6. Sebagai tambahan, jadi kenapa dia concentration juga besar karena dari automated mineralogy system ini kita calculate area sama densitas dari mineral itu sendiri. As mentioned, kita nggak bisa memberikan menjadikan automated mineralogy ini sebagai bukan alat. Dia memberikan support yang sangat esensial, sangat penting untuk kita sebagai user membuat keputusan. Jadi bukan mereka yang membuat keputusan, bukan sistem yang membuat keputusan. Mereka sebagai tools yang sangat powerful untuk memberikan kita keputusan dari berbagai dataset tadi. Oke, next. So that's all. Mungkin kalau ada yang mau bertanya, itu bisa di email atau on the next questions Q&A session. And next, please. Please stay karena saya mau kasih nggak terlalu kejutan kali ya. Oke, next. Jadi kami di geoscience coba trial di tin section karena kita penasaran. Sebelumnya kan Petro itu basisnya ya dari optical microscopy, behavioral on lighting systemnya aja. Jadi gimana sifat optisnya. Terus kalau kita upscale, kuantifikasi kayak gimana. Oke, next. Nah ini trial resultnya kami pada sampel sayatan tipis petrografi karbonat. Kita bisa mengkuantifikasi dari mineral-mineral tersendiri. Menurut saya ini sangat esensial ya, ternyata bisa jalan di karbonat juga gitu. Ini sebenarnya out of main topics, tapi saya pengen mengenalkan juga gitu, karena align sama sesi hari ini terkait automated mineralogy, bahwa di satu sampel kita bisa memberikan data yang banyak gitu. Dari sayatan kita dapat tekstur, dari AMICS kita bisa dapat kuantifikasinya, bahkan kuantifikasi visual porosity dan data mineraloginya itu kan esensial untuk menentukan bukan hanya mineral batuan ya, tapi juga post depositional proses atau diagenesis. Kalau di batuan buku kita bisa tahu paragenesanya dari tekstur juga mineralnya sendiri gitu. I think that's all. Menurut saya presentasi saya singkat sekali. Semoga memberikan banyak lagi gambaran apa itu automated mineralogy system. Sekali lagi terima kasih atas kesempatannya. Selamat pagi.
Selamat pagi Bapak. Terima kasih untuk presentasinya. Nih, jadi sangat menarik ya teman-teman bagaimana cara kerja AMICS untuk membantu identifikasi mineral, lalu untuk visualisasi data dari sampel. Nah, selanjutnya waktunya untuk sesi diskusi. Jadi kalau ada pertanyaan bisa diketik di kolom chat atau bisa langsung raise hand aja. Terima kasih. Oke Pak, ternyata ada yang langsung direct message ke saya. Jadi ada yang bertanya, AMICS itu bisa ngedeteksi liquid material nggak sih Pak? Kalau misalkan materialnya dan kalau material itu misalkan ketutup sama liquid, apakah masih bisa dibaca oleh AMICS? Terima kasih.
Oke, terima kasih pertanyaannya. Sorry, liquid ya?
Iya betul. Liquid
Oh,
material.
Jadi karena ini dilakukan di SEM yang mana mesti dalam kondisi vakum, jadi liquid itu tidak bisa.